Okay. La Hospital's rule. What the hell is this? Well, actually, it's... The way you pronounce this is Low-Pee-Tahl. Low-Pee-Tahl. Now, what on earth is this? Oh my god, a limit. We haven't seen these in so long. I thought we were done with the stupidity. Now, it seems a little disjointed that we did all this implicit differentiation, related rates, and then we go back to limits, but here it is. This is the next topic. Now, what you did back in the day, you first try to plug in, right? Plug in 1, 1. You get 0 to 0. This is called indeterminate form, meaning you can't determine it. Indeterminate. I'll write that in a minute. So what you had to do is you factored the top. You can't factor the bottom. So you factored the top. You crossed out the guy that was screwing you up, which was the x minus 1. Then you plugged in. And you got 2. No problem. Alright, so I've written another one here. Limits of indeterminate form. Remember, indeterminate means you can't determine it. If you try plugging in, one to the ninth is 1. 1 to any power is 1. Take away 1, you get 0. 1 minus 1 is 0. So you get 0 on top, 0 on the bottom. That's what indeterminate form is. 0 over 0. Indeterminate form is also infinity over infinity. We're not going to deal with that right now. So, how the hell do you factor this? Yeah, good luck with that. You can't. Not going to be able to factor this. So this is the point of Low-Pee-Tahl's rule. He gives you a very easy way to do limits without doing all the crazy trickery that we did way back in the day when I taught you how to do limits. Now, keep in mind, we didn't know what a derivative was or how to take a derivative back then. Now we do. So now we're going to be able to do a shortcut to do these limits. So this is Low-Pee-Tahl's rule. I'm just going to write LH for abbreviation. So Low-Pee-Tahl, not La Hospital. You can call it whatever the hell you want, though. I won't know. So if you have some limit here, that's a fraction. Remember, this is what's going to mess you up, is you get zeros on the bottom. But it's very important to understand you get 0 over 0. Not, 1 over 0 or 0 over 1. Those are not indeterminate form. It has to be 0 over 0. So when you have a limit that's a fraction and it doesn't work, you get 0 over 0. What you do is you take the derivative of the top dude, you take the derivative of the bottom dude, and then you just try plugging in. It's that simple. So I'm just writing the rule for you. You take the derivative of the top, you take the derivative of the bottom, then you try plugging in. If you get 0 over 0 again, then you do Low-Pee-Tahl's rule again. Then you take the derivative of the top again, take the derivative of the bottom again. You can keep doing this indefinitely. And at some point, it's going to work. You're not going to get 0 over 0, and you're going to get an answer, and that's how you do it. So I'm going to do that for this one. I'm going to take the derivative of the top, the derivative of the bottom, and then I'm going to try plugging in. When I take the derivative of the bottom here, you get a 1. Done. I don't have to worry about getting 0 on the bottom anymore. That's what's nice about Low-Pee-Tahl's rule. You just take derivative, and plug in. And again, you might be thinking, why the hell didn't you show us this all the time ago? But, you didn't know how to take derivatives. You had to know how to do all of the derivative techniques before you can do this. So that's why you had to learn all that stuff before you learned Low-Pee-Tahl's rule. So I'm going to work this example, then I'm going to work a couple more. So back to the example. We already know it's indeterminate. So I'm going to apply Low-Pee-Tahl's rule. I'm going to write LH, indicate that I'm applying the rule. Take the derivative of the top. The derivative of x9 is 9x8. Derivative of 1, constant, goes away. Derivative of x is 1. And derivative of negative 1 goes away because it's a constant. Now, plug in. It's this easy. Oh my god, it's just 9. Derivative of the top, derivative of the bottom, plug in. You're like, wow, this is so easy. And it is easy. They'll get a little more difficult. You might have some more complex derivatives there, which I'm going to show you in a moment. The moment is over. So, second example I'm going to work. Lim x goes to pi. Oh boy. Pi. I don't want to do pi. Cosine of pi is -1. Sine of 2 pi. Now, pi is 180. 2 pi is 360. Sine of 360 is 0. Aha. Indeterminate form. 0 over 0. You cannot determine. So, I'm going to use Low-Pee-Tahl's rule. I'm going to take the derivative of the top. I'm going to take the derivative of the bottom. Derivative of cosine is negative sine. Derivative of 1 goes away. Derivative of sine 2x. Chain rule action here. Derivative of sine 2x is cosine 2x. And then I have to take the derivative of the 2x. That's the chain rule part, right? Sine u. It's cosine u times du. So put the 2 in the front. Now you're going to plug in again. Sine of pi is 0. Cosine of 2 pi is 1. So 2 times 1. Oh man, how stupid, it comes out to 0. That's the answer. It's 0. But 0 over 0 is 0. No, it's not. 0 over 0 is 1. No, it's not. It's none of those things. It was indeterminate. Okay? You cannot determine it. So, took the derivative of the top, derivative of the bottom. This is important. This is your work. If you do these derivatives wrong, even if you somehow magically get this answer, I don't care. You have to have had the derivative correct. Okay? So, there's another example of Low-Pee-Tahl. I'm going to do one more before you are completely on your own. All right, the final example. I made it a little more complex. And you're thinking, oh, I thought this was going to be easy. I mean, it's easy when they're all x's, like x squared, x to the third. But they get more complex. First, I want to make sure it's indeterminate. Plug in 0 for x. You get ln1. Natural log, right? Plug in 0 for x there. You get e to the 0. Now, if you forgot, it's fine. You can whip out the calculator. Ln of 0 is 0. E to the 0 power is 1. Just make sure it's indeterminate. If you start doing Low-Pee-Tahl's rule, and it wasn't 0 over 0, Low-Pee-Tahl's rule isn't going to work. Low-Pee-Tahl's rule is only going to work if you get 0 over 0. It has to be indeterminate. So, same thing as the other two examples. I'm going to apply the Low-Pee-Tahl rule. And again, you got to be very careful here. First, remember to write lim until you plug in the derivative of ln u. It was du over u. So it's 1 over x plus 1. And the derivative of that goes on top. But what's the derivative of x plus 1? The derivative of x is 1. The derivative of 1 is 0. So that's on the top. What's the derivative of e to the u? It's e to the u du. So the derivative of e3x is e3x times 3. Not quite as simple, right? And the derivative of -1 is 0. Goes away. It's a constant. Now you're ready to plug in. This is too complicated. You get 1 over 0 plus 1. 3e to the 0. I don't know what to do. It's too complicated. This is 1 over 1, which is 1. E to the 0 is 1. Done. You get 1/3. There you go. So again, I confirmed that it was indeterminate by plugging in, making sure I get 0 over 0. You had to know that the natural log of 1 was 0. Your calculator can tell you. And I won't know if you're using one. So I got 0 over 0, so I did Low-Pee-Tahl. Derivative of ln u is du over u. Chain rule. Derivative of e to the u is e to the u du. Same thing, chain rule. So, the derivatives aren't going to be trivial. All right? They can get a little complicated. So, just got to be careful what you're doing. But these problems are not that hard. There's going to be a whole bunch of them on the worksheet. It's all the same thing. Make sure they're indeterminate. Make sure that you plug in to check. And take the derivative of the top, derivative of the bottom. If I were to get 0 over 0 again, I would do Low-Pee-Tahl's rule again. There are a couple examples on the worksheet that work out that way. All right? So all in all, compared to the topics we've done, this is not that hard. This is much, much easier than the last two things we did, which was implicit differentiation and related rates. So you get a little bit of a break doing something a little easier. So good luck.